Good day. My name is Roshanka Ranasinghe. I work in the Netherlands. My affiliations are here. I'm also currently heavily enrolled in the sixth assessment report of the IPCC, which is due out in August. So keep an eye out for that. I thank the organizers of this workshop for inviting me to speak a few words on this topic, which is very close to my heart. Congratulations also for the organizers for pulling together more than 300 people working on this topic, which is amazing. I remember when I started working on my PhD with Chari, Pattiaratchi in University of Western Australia, there weren't that much publications around. There was a few from John Largie, Jill Slinger, and them in South Africa, but that was mostly on the water quality side of things. There was one conference paper from Angus Gordon on the morphodynamics of seasonally open inlets, and that's where we started. So which also led me to having to develop a new model that can actually simulate the morphodynamics of these systems. So yeah, from there now in 22 years to see so many people working in this field is really nice. Okay, to go into my presentation. So why are we interested in looking at climate change impacts on these intermittent estuaries? They are mostly located in tropical and temperate regions of the world, as you would know. But these are also the regions where these climatic impact drivers are projected to change quite severely in the coming 30 years or so. So things like sea level rise, extreme sea levels, river flows are projected to change quite significantly by mid-century. So that's about 29 years from now. So not a long time left for us to look into these and come up with adaptation measures. So that's a bit of context and the challenges as far as I see them for assessing climate change impacts on intermittent estuaries. I have divided them into two sections. One is data. So more data will definitely help. So as many field campaigns as possible to collect data, which will not only improve our physical understanding of these systems, but also help us in things like model initialization, calibration, and validation. And what would also be nice is to have some kind of central data sharing platform that people could get data when they need from whichever system or whichever country that they are interested in. Another thing I think Sarah McSweeney started doing this in her studies, looking at remote sensing data, so satellite images and other Earth observation data to get an understanding of how these systems work and characterize them. But I think that there's much more to be done in that area. We are not exploiting all the freely available information currently available. There's things like Shoreline Monitor that was developed at Deltares and COSAT that was developed in UNSW, which we could use to really look at the medium to long-term behavior of these systems. Another thing that John Largie and I had a little chat about a couple of years ago when we had project meeting in Delft was the lack of any continent scale meta-analysis of intermittent estuary characteristics. That would be really helpful, and maybe it's a good idea for this community, which may lead to a few community papers on continent scale meta-analysis. So that's about data. About modeling, of course, there are many challenges, but due to time limitations, I will just concentrate on the two main challenges as I see them. On the short time scale, we have had some success in modeling using process-based models, the closure of inlets, as you may have seen in the presentation by my colleague Trang. We can now model inlet closure in a very realistic way with the right time scale, with the right dimensions. So, as seen by this figure. These results are published here in Duong et al. 2018 in Marine Geology. Anytime I refer to a paper in this presentation, I have provided a hyperlink so you can directly access that paper. So, but although we are able now to simulate inlet closure, inlet breaching is still something that I haven't seen any convincing results of. Here I have added a hyperlink to the artificial breaching of Wilson Inlet in 2020. I will not play that now, but you can have a look. You'll see that when these inlets are initially breached, it's a very complicated hydraulics. You have supercritical flow and hydraulic jumps, and simulating these things correctly is necessary to be able to predict what the stable dimensions of the inlet that we will end up with after a breaching event, artificial or natural. Until now, we have not been able to simulate this. I think mostly because of issues with making a good computational grid for models. There are certain limitations associated with making a grid, especially with these rectangular type grids. But now with Delft 3D flexible mesh, which allows different types of elements, triangles, rectangles, curvilinear grids, all those things can be combined. We should be able to make a nice grid that goes from coarse grid cells to very fine grid scales in the inlet channel. And that should be able to handle these complex hydraulics. So that's a nice thing to try in the next period ahead. Of course, the biggest challenge that we have been facing for many years is our inability to simulate 100 years of climate change timescales using process-based models. We have, however, made some significant steps forward. If you look at the last 22 years, in 1999, it's when I developed my model, which could then at that time handle 3 months of morphodynamics with combined wave tide river flow forcing. And from there, in 2004, Giles Lesser presented this updated version of Delft 3D, which is still operation mostly in that form. And they could simulate a 5 years continuous simulation of inlet dynamics with waves, tides, and river flows. After that, we kind of moved away into reduced complexity simulations because of the inability of the process-based models to simulate 100 years. So then there has been a number of developments in that area, and also you saw earlier with Chang's simulation that she actually used process-based models, but with a snapshot approach, which simulates the beginning and the end period with some approximations in the middle to get there. And in 2021, so this year, there's a couple of things that came out with one of my PhD students, with Janaka Bamunawala, who developed a reduced complexity model again to be able to simulate the shoreline change on inlet interrupted coastlines. However, there was no real simulation of the closure of inlets. We are also currently working on a paper with Trang again to present a reduced complexity model that can simulate inlet stability over a 100-year period. So that model should be able to tell us at which point in time in the next 100 years inlet is likely to close or stay open. But that's still a work in progress. So as I said, there's been some developments, but of course the holy grail is to be able to simulate 100 years using a process-based model like Delft 3D or Mike 21, while also preserving seasonal forcing effects like wave seasonality and river flow seasonality. We have been doing some brainstorming about such a model, and we think these are the kind of features that would enable us to get there. But yeah, it's still very much at the developmental stage, so it's still at the stage where we are developing equations and process and modeling methodologies. But we are working very hard on it. As you can see, here is my colleague in Delft, Dano, Roelvink, and me really working hard on it in a neighborhood bar. I think this would be a really nice topic for a PhD student who's brave enough to delve into Delft 3D. And work with the code, change some things around. So for more details on what I'm doing here in Delft with my colleagues from different organizations, I invite you to have a look at my research program here and also this short video. Of course, there's a lot of people involved in what we are doing on this in Delft and in the Netherlands on this topic. I will not read out all the names, you can read them here. So a big thank you to all of them, and also thank you all for your attention. Have a good day.